So you will definitely have a problem like this on your test. That's why it's a warm-up. We have a cube with side length 4 circumscribed about a sphere. What is the difference in the two solids' volumes? A cube circumscribed about a sphere. Can you try to draw that? So I'll do the best I can. It might not look that great, but so we got to get our cube. Yikes. My cube is going to be majorly leaning over. And we have a sphere inside. Not a big deal what your picture looks like. But the key word is circumscribed. That means the sphere is touching every face of the cube. The sphere is touching every face of the cube. Let's see. So this right here would not quite be circumscribed, because notice my sphere isn't touching every face, it's just kind of inside the cube, but the sphere is inscribed, and so it's going to touch every side. So that means that the side of the cube is the diameter of the sphere, okay? So what is the difference in their volumes? We're going to find the volume of the cube, and we're going to subtract the volume of the sphere. And then we'll find out what the empty space is. All right, volume of a cube, base times height. That's the area of the base, and that's the height. Or, of course, hopefully you know, you can just think of it as 4 cubed. That's where the word cubed comes from. It's the volume of a cube. So you take the side and you cube it. Okay, volume of the sphere. This formula is a little bit more complicated. 4/3 pi r cubed. So notice I used r. R is 2 because the diameter is 4. Okay? So we have 4 cubed minus 4/3 times 2 to the 3rd. 4/3 times 8. So not the prettiest answer we've ever seen. No units. Cool? So, of course, we always put our answers exact. If your test happens to ask for it rounded, then you could plug that into your calculator and press pi. But unless otherwise noted, we're not going to press pi. So your homework last night was spheres. So here are the spheres, evens, answers. My favorite one was Roman numeral 3, number 4. That one's really fun. Do you want me, I'll probably work this one no matter what. Is there another one you need me to work? All right, let's look at the very last problem on your homework, number 4. I really like this one because you have to really use what you know about the radii of the sphere and the height of the cylinder. So we have a can of tennis balls, and there's 3 balls. Sorry, they're not all congruent in my picture, but pretend they are. Okay, so we are going to assume that the balls touch both bases of the cylinder. We're going to assume that they are kind of inscribed, although that's not the right word. We're going to find the ratio of the volume of the can to the volume of the 3 balls. So we want to do volume of the can to volume of the 3 balls. Okay? So we were not given any numbers. We were not given a radius. We were not given a height. So we're going to hope that some of the variables cancel. That way we can come up with a ratio, a numerical ratio. Let's do the volume of the 3 balls first. We're going to do this one first. How do you find the volume of a sphere? 4/3 pi r cubed. But there's 3 tennis balls in a can, which most of them do come with 3. And so we're going to put a 3 in front. We're going to triple that number because there's 3 spheres. Okay, here's where it gets tricky. The volume of the can. Now, the volume of a cylinder is the area of the base times the height. Now, if we're trying to get this into a ratio, that ends up being numerical with no letters in it, no variables, we can't have two different variables. Well, we can't have one that doesn't cancel. So the height is a problem here. H is a problem. We need to try to write H in terms of R. So I want to know how many radiuses, radii, equal the height of that cone. How many radiuses, radii, equal the height of the cone? Oh, y'all were ready, huh? Okay, so we have radius, 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 radius. The height is really 6 radii. That is so cool. So I'm going to remove H, and I'm going to put 6R. And now we're going to clean this up a bit. So in the numerator, we have a 6, we have a pi, and what's R squared times R? So that's the numerator. In the denominator, the 3's cancel, so we have 4, then we have pi, then we have R cubed. Look at what happens, guys. This problem's so fun. Pi's are gone, the R cubes are gone, and we're left with 6 over 4, which is 3 halves. All that work and we came up with one final answer. The ratio is 3 to 2. Cool, huh? It got so beautiful so fast. That was a good way to phrase that. Let's jump right into today's lesson. It is called PAV Ratios, or PAV, Perimeter Area Volume Ratio. Perimeter Area Volume Ratios. Oops. This is old news. We already learned this in the similarity unit, so this is just a refresher. Perimeter Area Volume Ratios. So the ratio of the perimeters, aka the sides, or really any segment at all, the ratio is simply A to B. A to the 1 to B to the 1. The ratio of the surface areas is A squared to B squared. And of course the ratio of the volumes is A cubed to B cubed. This is the 1D, 2D, 3D lesson that we've had before. Let's try some problems. We're going to start with just a table. This is really basic, simple, straightforward. Let's all do row 1. Let's all do row 1. If I tell you the similarity ratio is 1 to 2, what's the ratio of the surface areas? 1 to 4, right? Did we have to actually find the surface areas? No. We are talking about the ratio. The ratio of the volumes? Any questions so far? So when a problem asks you, because you always forget to use this, when a problem asks you, okay, I took 2 cubes and I doubled the sides. I doubled the side of the cube. What happened to the volume? And do you know what people say? They say it was doubled. But now you know the answer. If I double the side, what happens to the volume? It is 8 times bigger. Because when you double the sides of a cube, you're doubling the length, you're doubling the width, and you're doubling the height. You're doubling 3 dimensions, not just 1 dimension. Okay? So if I say, in a story problem, so-and-so doubled the side of a cube, what happened to the volume? You would say the volume was 8 times bigger. All right, let's do the next one. 3 to 5 would, of course, become 9 to 25. And then we're cubing them. All right, now we're going to work backwards. The opposite of squaring something is square rooting. So we're going to square root this one to get 7 to 9. You always reduce if necessary, but that's not necessary here. This one's going to be quite large. We okay here? Cubing 7, cubing 9. And how do we go backwards from volume? How do we go from volume to perimeter? Remember the buttons to press? Math 4. Cube root. Very good. So math 4. Cube root of 125 is 5. Cube root of 512 is 8. Moving on. Okay, here's where we put it to use in a story problem. Well, it's not really a story quite yet. The edges of a large cube are 4 times longer than the edges of a small cube. Keyword, edges. Here are the important things. An edge is just a side. An edge is one-dimensional. How many more times greater is the volume? So now you know what to do. How many times greater is the volume? So if I am quadrupling my sides, then what am I doing to my volume? If I want to make this 3D, I have to turn my 4 into 3D. It needs to go from 4 to the 1 to 4 to the 3. Good. So how much greater is the volume? It is 64 times greater. Because you're not just changing one of the sides times 4. You're changing the length, the width, and the height by 4 for 3 of the dimensions. Here's another one. We're getting multicultural here. Ying Yu bought a rectangular box to display her doll collection. She decided to exchange the box for a similar one that had double the dimensions. Here's keyword. Double and dimension. Dimension means it's like a side or a height. It means it's 1D, and double means times 2. How does the volume of the box compare to the volume of the smaller one? So we know that we doubled our sides. That's our 1D. But we want to go 3D on it. We want to go 3D, so we need to change the exponent to a 3 instead. So how much more is the volume? It is 8 times as large. 2 to the third is 8. Two similar vases have surface areas of 36 inches squared and 100 inches squared. What is their similarity ratio? And then we'll do B next. Okay, so similarity ratio means, what is their 1D ratio? That's what it means, their 1D comparison. So it doesn't matter which one we put first, doesn't matter. So I have 36 over 100, and I'm going to put my bubble on top. I always put little bubbles, so that I know what dimension I'm working in. It is surface area, so I'm working in 2D. Now, you have two choices. You can reduce that and then square root it, or you can square root it and reduce it. It doesn't matter. If I want to make this 1D, which I do, I want to square root these. And then we always simplify. You never ask, do I need to simplify my answer? Because the answer is always yes. You always simplify your answer. So the similarity ratio is 3 to 5. Now, if the height of the larger vase, if the larger vase has a height of 15, what's the height of the smaller? So height, how many dimensions is height? 1D, 2D, 3D. Oh, Graham, you're already answering it. Height is one-dimensional. So we get to use, we don't want to use this ratio, 36 and 100. We don't want to use that one because that one's 2D. We want to use our 3 to 5 because that's 1D. So 3 is to 5, that's 1D, as X is to 15. And this is kind of silly. Oh, sorry, 1. They're both 1D, so you're allowed to cross multiply. Or you can just say 5 times 3 is 15. 3 times 3 is... So we set up a proportion and we cross multiply. Never cross multiply until you've checked to make sure both ratios are in the same dimension. Okay, last one of the day. Your coffee thermos holds 3 cups of coffee. You probably don't drink coffee yet a whole lot, so pretend it's your water thermos. Your water thermos holds 3 cups of water. Your friend's water thermos is twice as tall, but has half of the radius of yours. How much coffee does their thermos hold? Dun, dun, dun. Give you a minute to think about this one because I want you to reason through it without me showing you. This is the first time we've done one like this. I'm going to give you a minute to think. So your coffee thermos holds 3 cups of coffee. Are are we talking about surface area or volume? Let's just get that straight first. Volume, okay, because we're holding a liquid, so totally volume. Okay, so we want to compare the volume of both of these. Now, we're going to assume they're both perfect cylinders, although I know you could argue with me, but I bet the inside where it holds the actual water is a perfect cylinder. So let's compare the volume formula. Okay, so the volume of a cylinder is base times height. So that's going to be the volume of your cup. This is yours. Now let's look at the volume of your friend's cup. Your friend's cup is twice as tall. So instead of H, I'm going to put 2H. It's got to be a really tall coffee cup. So by the way, this one's yours. And this is your friend's because it's twice as tall. But it has half the radius. So instead of R, I'm going to put 1/2 R. I didn't leave myself enough room. So does everyone see what I did to the formula? I substituted 2H in for H because double the height, and I substituted 1/2 R in for R because half the radius. Let's clean this up a bit. This is going to equal pi 1/4 R squared to H. Are we okay where I got the 1/4 from? 1/2 squared is 1/4. You have to square the coefficient and the variable. Let's keep cleaning this up. The 1/4 and the 2 become 1/2. So here's the volume of yours, pi R squared H, and there's the volume of your friend's. How much coffee does theirs hold? Look at those two formulas. Pi R squared H and 1/2 pi R squared H. Theirs holds half the liquid yours does. Half. So theirs holds 1.5 cups of water or coffee or whatever liquid we're putting into our thermos. What's cool is that it's twice as tall and half. So you're like, oh, the 2 and the 1/2, those just cancel. It's going to hold the same amount, right? But be careful. The H in the formula is not being squared, and the R is being squared. So that makes a big difference. You're halving the radius, but the radius is being squared, so you're really 1/4ing it. Hope that makes sense. It was a good challenge problem. Okay, so we are done with this lesson.